Hi, and welcome to a special edition of Blockchain Fundamentals with Bill Laboon. Thanks to the lockdown, which is hitting us here in Switzerland, as I'm sure it has hit many of you all over the world. I will be recording this myself. I'm going to apologize ahead of time as I am certainly not a videographer, but hopefully this will give you all of the information that you need and you can ignore the fact that I'm sitting down in a booth as opposed to standing at a lectern. So today we're going to discuss mining in a little bit more in depth, and specifically the mining that is done in Bitcoin, because there are some variations on mining, and we'll talk about some of these different kinds of proof of work and different ways of arranging blocks, etc. However, as we've done often through this course, Bitcoin is really the first modern blockchain, and in some ways of the ones out there, it's one of the more simple and straightforward ones. And I think it behooves everybody in the blockchain space to at least understand the basics of how Bitcoin does mining. However, any proof of work system that does mining, you are going to see very, very similar features throughout and very similar concepts, even if they're not exactly the same. So what does it mean to be a miner on Bitcoin? So some of this we already discussed in the last lecture. But basically, if you're a miner, what you're going to do is listen for any transactions that are being sent out to the Bitcoin network. That means you're going to maintain a transaction pool, or as it's sometimes called, the mempool or memory pool. So this is just a list of transactions that have not yet been included in a block in the blockchain. So they're transactions that are have been broadcast, have been made, but are not yet part of the blockchain. You, as a miner, are going to make sure that you are up to date for this with this blockchain. You're going to listen to see if any other miners have produced new blocks, and if they're valid, add them to their chain. You are going to try to assemble a candidate block. So what this means is that you are going to try to produce a block that other miners will accept. And the way to do this, you're going to take some of the transactions that are in your mempool and put them all together into a block. And additionally, create a block in such a way where the hash of that block, and we'll talk about the specific hash function, SHA-256, in a moment, where the hash of that block is less than the target. And if not, generate a new candidate block. If you find one, if your hash of the block is less than the target, you can broadcast that block. Otherwise, you keep trying it again. And what's the benefit is that you can generate an additional transaction as part of that block, which is going to give you two things. One, you're going to get the reward for creating that block, which is currently 6.25 Bitcoin. It started at 50, but there have been 3 halvings so far where it's gone down from 50 to 25, 25 to 12.5, 12.5 to 6.25, as well as any transaction fees that were included in any of the transactions that you sent. And you can take all of these values and send them to whatever address you want. I mean, if you want to be nice, you could send it to my address, but you probably are going to want to send it to an address that you control. So if you're looking in the transaction pool, the mempool, you're probably going to want to try to optimize for the highest transaction fees that you can, and construct a Merkle tree of these transactions. Now, there's no necessity for doing this. If you would like to include transactions that have included no transaction fee or have very low transaction fees, and would prefer to include those over other ones, that is certainly your right. But usually, if you're trying to produce a block, if including one transaction would give you, let's say, a tenth of a Bitcoin, and another transaction will give you a millionth of a Bitcoin, well, most rational miners are going to want to include the one that gives you the tenth of a Bitcoin over the millionth of a Bitcoin. So here we can see how transaction fees work, right? Really from the miner's perspective, is there's only a limited amount of space in each block. And if you have the option to include transaction 1, which has a very high transaction fee, or transaction 2, which is a very low transaction fee, and you're going to get that transaction fee, you're probably going to include the higher transaction fee over the lower one. And so this is why when you are using Bitcoin, if you set a high transaction fee, it is much more likely that your transaction will go through more quickly, because these miners who are acting in their own best interest are going to want to include that first. Again, though, just like many things in Bitcoin, this is stochastic, right? It could be that your transaction, even if it has a higher transaction fee, doesn't work for one reason or another in one block and gets added to a different one, or just that a miner didn't see your block in time. But generally, if you're a miner, you're trying to make optimize for the highest transaction fees. This is often very difficult because transactions are also of different sizes, and this is basically a version of the weighted knapsack problem, which means that it is very difficult to solve in an optimal way. So there are a lot of heuristics, but generally higher transaction fees more likely to go into a block fast. It means your transaction will go through faster. So once we have constructed a Merkle tree using these transactions, we're going to take the Merkle root, so the root of that top hash, and include that in our block that we're producing. So you'll see we have a couple of other bits of data we're going to include in our block here, including the hash of the previous block. So if you remember how a blockchain works, we need to include some data from that to keep the chain running, to make sure that we can verify that this block does go, block A goes first, then block B, then block C, etc. We have the time, so this is seconds since the epoch. We have how many fees are included, and we're going to have the big list of all the transactions. So I've got that TX, the opening of that array, right there, although I did not include every single transaction in this block, and I also eliminated some of the other data in here. So we now have this candidate block, something that is potentially valid. We've put together a Merkle root of all the transactions that we've put into a Merkle tree. We have set the time and all the other relevant metadata. And we also have this ability to add a nonce. So nonce you'll hear used in a couple of different ways in the blockchain world. I think it's one of those rather strange words that people are going to use in different ways. It certainly means something different in Ethereum here, but than in Bitcoin. But in Bitcoin, this nonce is some number from 0 to 2 to the 32nd minus 1. So it's basically a 32-bit unsigned integer. And this is going to give us the ability to, with the same candidate block, try different values that will produce a low enough hash. So we can try our candidate block with a nonce of 0, and then with a nonce of 1, which is going to give us a totally different hash, 2, 3, etc. And remember, if any of these are found to be lower than the target, then we have a valid block. So you may ask yourself, based on some of the other discussions we've had about mining here, only 2 to the 32nd nonces, that seems like a relatively small number. That's basically 4 billion. And we're looking at the Ethereum network, the Bitcoin network is looking at quadrillions of possible hashes every second. It's hashing through quadrillions of potential blocks. So you may say, well, only 4 billion. That is, if you're a math major, that's less than quadrillions. So what can we do if we go through all of these values and don't find a valid block with a low enough hash? Well, there are always other ways to modify this candidate block. So probably the easiest and most easy to understand thing we can do is just use a different subset of transactions. So remember our transaction pool has lots and lots of different transactions in it. It's very rare in the modern era for there to be so few transactions in the transaction pool that we would use up all of them. There's usually a bunch waiting to be put into into a candidate block. So one thing you could do, instead of taking transactions A, B, C, and D, you try maybe C, D, E, and F, or F, G, and H. And this is why, remember I said that even though generally miners are going to try to put the highest transaction fee transactions in a block, not all the time, because it could be that they were unable, using these highest transaction fee transactions, they may have been unable to produce a valid block, and so they try using some of the other transactions in the transaction pool. You can modify the Coinbase attribute. So this is just an unused script sig that allows you to put in basically arbitrary data. So you might want to try to change that as well. We could generate a new address and send our Coinbase to a different address. Get our block rewards and put them to a different address. That will modify the hash. We can modify the timestamp. Now, we can't set this to any time we want, but we do have some leniency in exactly what time it is, right? So we are allowed to modify this slightly as long as it's the timestamp's less than 2 hours since the last block. Then we could modify the timestamp, which would also modify the hash. So we can see here that there are a lot of different ways to modify the hash besides just the nonce. There are a lot of different things we can do to try to get a hash below that target value. So once we have done that, which is going to probably take a while, we want to generally broadcast it as soon as we can to the network, because this is a race, right? If a node sees that there are 2 blocks at the same height that have both been generated and built from the already existing canonical chain, then the first one they see, they're going to assume is the valid one. So we really want to get this out there as soon as we can, so that others will mine on our block. So if they see block A and block B, I'm block A here, then and others start mining on that, and everyone ignores this, well, this block gets orphaned and goes away, which means that our rewards for mining it go away. And so there is a built-in incentive to build on the first block that you see. So generally, and we'll talk about some potential exceptions to this a little bit later in the lecture, you really want to get that block out as soon as you can. It's a valid block. It's going to give you rewards if other people accept it. Just a little side note here. How do you know what that target is that is supposed to be your hash should be less than? So this is actually calculated from a variable called the mining difficulty, which changes every 2016 blocks. So every 2016 blocks, there is a calculation to set the difficulty for this next era. And it's calculated by taking the previous difficulty by times 2016 times 10 minutes and dividing it by the time that it took to mine the last 2016 blocks. So in a nutshell, what this equation is doing is trying to get Bitcoin to a place where the mean block production time is 10 minutes. If miners are generating over the course of 2016 blocks, if they're generating blocks every 5 minutes, let's say, well, there's obviously a little bit too much hash power here for the difficulty. And so we're going to increase the difficulty to bring the mean time up to 10 minutes. Conversely, if their miners are mining every, let's say, 20 minutes, then the difficulty is too hard and we should reduce it. They're spending too much time generating blocks. So either way, the difficulty is sort of self-correcting every 2016 blocks. And the difficulty is just the maximum target divided by the current target. Or we could say the target is equal to the maximum possible target divided by the difficulty. And so by looking at this, which this data is, this difficulty is included in the blockchain, we can calculate out what the target is going to be. So what is this particular hash function? Well, it's SHA-256. So SHA stands for Secure Hashing Algorithm. It's part of NSA's SHA-2 series of cryptographic hashes. So you may have seen a couple of other SHA hashes besides SHA-256. SHA-256 creates a 256-bit output. Because this was created by the U.S. National Security Agency, there are some conspiracy theories about it. However, a lot of, as you can imagine, right, anything that's created by a government, especially the National Security Agency, people may be a little suspicious of it. But all of the information is public knowledge about the hash, and a lot of people have reviewed it. A lot of people that are excellent cryptographers and have found nothing wrong with it, nothing major wrong with it so far. So the actual hash, when I talk about like the hash of a block, is not just SHA-256. It's actually the SHA-256 hash of the SHA-256 hash. So if I have some block, I'm going to take the hash of that, and then I'm going to hash the result of that. So it's like the hash of the hash. So for instance, if my hash was 74321 ... I would take the hash of 74321 as the final hash. So SHA-256 is a pretty standard Merkle-Damgard construction. There are some very minor twists compared to the one that we saw, or if you have done the exercise, the SHA-256 exercise. It is slightly different, but it's the same basic idea. Output, as I've already mentioned, is 256 bits, and the block size is 512 bits. The initialization vector, which is also going to be 256 bits, it consists of the fractional parts of the cube roots of the first 64 primes. And the reason this was set as the IV is to avoid any accusations of backdooring values, that there's some sort of weakness that the NSA has hidden in it. Strengthening, which if you remember in our exercise, was just adding zeros to the end of the string to make the last to make sure the last block was the right size. Interestingly, SHA-256 puts a 1 and then as many zeros to get up to 448 bits out of the 512 bits, the block size, followed by a 64-bit length of the string. So that is, how long was this string represented as a 64-bit unsigned integer, and that goes at the end of the padding. If you're interested, there's a link here to somebody who decided to mine Bitcoin with pencil and paper and walk through the entire hash process. So you also can walk through by hand if you're interested. The goal for miners, you may have heard of hash power. So, excuse me, that's the miners, really their edge is, are they able to compute as many SHA-256 double hashes as possible in as short a time as possible in order to maximize their block production. So the by hand rate for doing this is about 0.67 hashes per day. So that is, it takes about a day and a half to calculate one hash by hand. As you can imagine, that would not be an optimal way to mine Bitcoin, because by the time that you actually are able to produce even a single hash, well, many other blocks have occurred since then, if the blocks are being produced at a mean time of 1 every 10 minutes. So your goal really as a miner is to do this as quickly as possible. So you're not going to want to do it by hand, but luckily we have these amazing devices that are really good at doing math over and over and over again, called computers. So if you read the original Bitcoin white paper, which I recommend you do, it's relatively short, and if you've survived till this point in my lectures, you really should read the original white paper. It's not a difficult read. Satoshi seemed to really imply that most people that use Bitcoin would also mine, and that would be a major way of obtaining Bitcoin. So the idea is, every CPU was like one vote in the network. And with well-optimized software on a regular desktop, you can get several tens of millions of hashes per second, which is a respectable amount of computing power that it would be being used to protect the network. Because remember, the real reason for this mining, it's nice that it gives people Bitcoin or whatever tokens that they use. However, the real need for this is securing the network. When you're mining, you are making sure that somebody else, in order to try to come up with an alternative solution to the canonical chain, is going to have to do even more work than you. However, so for a while in the very early days, about the first year or so, many people would mine Bitcoin using their just regular computers. When they went to sleep, they would turn on their computer, let Bitcoin mine. But after a while, GPU mining became popular. So GPUs, graphical processing units, they basically have a lot of benefits to mining, since when you are running a simple hash function over and over again, it's not using a lot of really complex procedures. It's not using a lot of memory accesses. It's not doing a lot of stuff that a CPU, a central processing unit, is optimized for. And GPUs also are often parallelized. They can do the same operation or similar operations in lots of them at the same time. And so this was a really good fit for mining, because it provided allow you to do these relatively simple calculations over and over and over again, and doing them in parallel. So when somebody realized that you could do this, it actually took Satoshi by surprise. When he mentioned, he was sort of shocked, if reading between the lines in his Bitcoin talk post, that he had there were some people that had massive amounts of hash power on the network, because they were using GPUs. And when they explained what they were doing, he was sort of shocked that this was possible. And so there was an era where most people that were mining started using GPUs, because it was so much more efficient and powerful than just using your regular computer. And if you set up your computer correctly, you could have multiple GPUs on the same computer. Just put them in different slots and send the work out to all of them. So this was the era of Bitcoin mining rigs, that people would set these computers that had multiple GPUs attached to them, and mine as many Bitcoin. So we really still were in the hobbyist phase of mining in 2010, 2011, that era. However, soon after that, there was another sort of order of magnitude increase, as people realized that while GPUs are better than CPUs for mining, they're still not optimized. They're not perfect for it. There's a lot of superfluous hardware in most off-the-shelf GPUs. So there's a reason they're graphical processing units. They're not SHA-256 processing units. So around the end of 2011, people started using these FPGAs, field programmable gate arrays. You can think of these as basically programmable integrated circuits. So you could program these ICs, these FPGAs rather, to act like they were specific hardwired ICs. And this gave another order of magnitude performance increase. The problem with FPGAs, as people discovered soon, is that they are, one, relatively expensive, so there wasn't quite as much return on investment from using them as you might think, and they were also very prone to failure. However, people then realized that you could just actually, instead of using an FPGA and programming it, you actually could, just hardwire this stuff, have specialized hardware that's just for mining Bitcoin. And this was the era of ASICs, which is where we are today, application-specific integrated circuits. So these are specialized computers that can really do nothing but mine Bitcoin. If Bitcoin disappeared from the face of the earth tomorrow, these would be just very expensive space heaters. And improvements came extremely quickly in the early days as people discovered tips and tricks, as well as just with Moore's law in general, making computing power more easily accessible. They very quickly they just left all other ways of mining in the dust. So nowadays, if you are at all hoping to mine profitably, you are using an ASIC. And in fact, you are probably using the latest generation of ASICs. So even these early generations are just woefully outmatched in terms of how much hash power they provide for how much electricity you have to give to them. So once we find newer generation mining hardware, then the old hardware rapidly just becomes useless. However, during the time that they are useful, they are providing an immense amount of hash power to the Bitcoin network. So remember, the reason that we're doing all of this is not, we, the Bitcoin community, the reason that we are doing all of this is not so that we can give rewards to people. It's to make sure that the network is secure. Okay? So what we do to make sure that people are not cheating and not trying to produce invalid blocks is we force them to do this proof of work. They have to spend this electricity. So they've got skin in the game that if they try to do bad things that other nodes aren't going to accept, if they try to pass off an invalid block or a block that's not on the canonical chain or anything like that, well, the other nodes will just ignore them and continue without them. And they just spent a lot of hash power to, a lot of electricity. They spent a lot of money, in other words, to actually produce this block. And if they're not getting anything for it, well, what's the use? So it's a relatively simple and straightforward system that works pretty well, but it comes at a real cost. So Bitcoin uses an immense amount of electricity. So again, approximately equal to Austria or Switzerland, like a pretty massive amount of electricity to secure the network. Okay? So there are other systems that will talk about that don't use proof of work to secure the network, but have other ways of providing skin in the game, such as proof of stake. But let's continue just to talk about proof of work here for a moment. So could we increase efficiency? And we certainly can. As I've already mentioned, we've gone from CPUs, which are more efficient than doing things by hand, the GPUs to FPGAs to ASICs. But as soon as we figure out a more efficient way, as one person figures out a more efficient way to do this, then others are also going to use that more efficient way, right? As soon as they figure out about it. So it's a Red Queen's race, as we say. You have to go faster just to stay still. If you want to have a certain percentage of the network, let's say you want to have 1% of all the hash power on the Bitcoin network, as others, find more ways to be efficient, as long as it's profitable, they are going to increase their hash rate. They're going to mine more. They're not going to just step back because you want to. And mining is a zero-sum game in some sense. All of the miners are competing against each other. So even if you're more efficient, that doesn't mean the network as a whole will be more efficient. Just more hash power will be added. So that's great in terms of security. The network will be even more secure. But again, we've got those trade-offs, right? That's a lot of electricity that we spend. And there are limits on efficiency. Now Landauer's principle is the absolute limits of what a device made of matter can compute in terms of thermodynamic efficiency. Now we're still nowhere near that limit. However, that is something that is eventually a concern. If we're using proof of work, eventually we will get to a point where there is a limit on efficiency. We cannot become any more efficient without breaking the known laws of physics. So again, as I already mentioned, there are other ways of avoiding this, right? So there are other systems that don't use proof of work, but we'll come back and talk about those later. So then if we're using all of this electricity, is it really wasting that electricity? So this is a really good question, right? Any payment system that you use is going to require some energy. Again, in the physical definition, physics definition of energy. If you want to go back to the gold system, you're going to have to dig the gold out of the ground. If you want to run a bank, well, you need to store all the information for the bank and have bank tellers, etc. Even printing dollar bills, it doesn't seem like would be that big of a deal, right? Money printer, go burr. But even that, producing the dollar bills and shipping them to places and having people accept them, and anti-counterfeiting systems, there are a lot of details involved in using any payment system. There's a lot of energy involved. And so one way of thinking about mining is really, well, that's just Bitcoin. That's its way of securing the network, right? That if anyone wants to attack it in a double spend attack, a 51% attack, they're going to need to use at least somewhat close to an equivalent amount of energy. Okay? So one way to, and the more energy we use, that means the more difficult it's going to be to attack. Because if I'm using, let's say, 50% of the Earth's electricity usage to secure the network, and how else is someone else going to get more than 50% for me to access it? So another way of thinking about these is that these mining rewards are basically stored electricity. So if you do have electricity that can't be used for a better usage, that's going to give you more rewards, you can instead choose to use that electricity to mine Bitcoin. And there are some ways that people are using to make Bitcoin mining less wasteful, because anytime you make Bitcoin mining more efficient, you are directly contributing to your bottom line. So there are places that Bitcoin miners that are using renewable energy or otherwise wasted electricity. So they'll come online whenever a dam, for instance, is producing too much power for the grid. It needs to send that power somewhere. Well, send it to mine Bitcoin. There are some places that are using Bitcoin miners as space heaters, right? So that the generated heat that a miner produces, it has to go somewhere. Well, we could do things with that. People need warm houses in the winter, for instance. So there are ways to make it less wasteful, and Bitcoin miners are in fact incentivized to make it as little wasteful as possible. All right. So given all of this and even my description of how it works, if you still want to mine Bitcoin, so you go out, you buy $10,000 worth of ASICs from Bitmain, let's say, or whoever I don't mean to be providing a specific endorsement of any company, but you go out, you buy some ASICs. You start paying an extra $500 a month on your electricity bill. Okay? But if you do this, your income is rather sporadic. Remember, finding a block is it's probabilistic. You don't know when you're going to find a block and thus get rewards, but you have these expenses coming in. So it could be that you spend $500 every month, but you go for a year without finding a block. So great, you spent $16,000 last year and you didn't get a return. Or theoretically, you set up your rig and you find 2 blocks in a row and get $170,000 worth of block rewards. Both options are possible. But generally, if you're running this like a business, then you want to reduce your variance. So what if you could work with others to make a collective, almost like a business or a partnership, and you all pitched into work and smooth your earnings? So this is a mining pool. It's a collection of miners generally run by a pool manager who's going to take a small cut of the rewards in return for managing all of this. So all of you are going to pool your hash power and try to find a block. And if you find it, it's going to go to the pool manager, who then divvies it out amongst all of the different miners in the pool. But how do you prove that you have so much hash power? What if I tell you, oh yeah, I've got thousands and thousands and thousands of Bitcoin miners in the back. I'm spending tons of money on electricity. I'm not. Are they going to believe you? No. But you can prove that you're doing it by turning in what we call shares. So here, not only are you going to let the pool manager know once you've found a block, but you're also going to turn in near misses. So where the hash of the block was not less than the target, but was close to the target. So target plus some value. The only way to find these is by doing the work. So again, probabilistically, you are very unlikely to have a lot of these near misses, these shares, unless you're actually doing the work. Again, it's astronomically unlikely that you would not have the hash power, but are somehow also able to come up with all of these near misses. And thanks to the law of large numbers, we actually can get the pool manager can get a very good idea of what your hash power is just based on these verifiable near misses that you turn in. So there are a couple of different ways that the payout can occur. I don't think, unless you're really interested in mining, it makes sense to go really in depth on these. But basically the idea is the more shares you submit, the higher the reward you're going to get. So generally, again, there are some differences in this, but if you have a lot of hash power, you're spending a lot of electricity and time and energy producing these, you will get a higher percentage of the rewards that are paid out for a mining pool. So the first time I ever taught this, a clever student said, well, why wouldn't I just withhold a block, when I find one, or have it send it to me? Well, there actually are some attacks, a block withholding attack, if you're trying to attack a mining pool and get them to sort of waste time, only turn in near misses. But it's honestly not an attack we see often in the wild. And really, from a game theory perspective, you're wasting hash power. So if you have some non-economic reason for attacking this mining pool where it'll think it has more hash power than it really does, generally, people are rational actors. If they can make money, they're going to do so. They're going to want to get Bitcoin. You can't modify the what else could you do? Theoretically, I could find a block and then say, oh, well, now that I found it, instead of playing nice with the cooperative, instead, what if I change the payout address to me and just submit this myself? But remember, if you change this address of where your block rewards are going to, you've just modified the Merkle root. Because that modifies the payout address. And now you no longer have a block whose hash is less than the target. So again, once again, if you don't play along, you're really just acting against your own best interests. So pools tend to work pretty well. However, there are some problems, right? Pools can be too powerful. So remember that a pool really is acting under the supervision of a pool manager, but generally you can think of them as one big miner with a lot of hash power, even though there are individuals. It's one entity. And there actually have been cases where pools had a greater amount, more than 50% of the hash power. So Ghash.io in 2014 had this, and they intentionally reduced their hash to make sure that people still trusted the Bitcoin network. There are some theories that there are large mining pools or miners that are hash laundering. So they're joining, they're hiding their hash power by joining multiple pools, which again is relatively trivial to do. But even without thinking about hash laundering, there are still very large pools that it only takes a few of them together to get over 50%. But lately, there haven't been any that have really been over 50% of total hash power in the last few years. Although miner consolidation is certainly something that should be thought about and considered, because mining is definitely one of those things that has a lot of economy of scale and so lends itself to these large mining collectives forming. So overall, is it good or bad that mining pools exist? Well, there are a lot of pros, because if you're just starting out at mining, it's going to reduce your variance to be part of a pool, which means it's easier for new miners to get involved. That's going to help decentralization. It's an easy way to make sure the network stays upgraded, because you can't join the pool unless you're running the latest version of Bitcoin software. It provides some checkpoints. But those pros also come with cons, like everything else. So it is another form of centralization. It reduces the number of fully validating Bitcoin nodes, since really only one is necessary per pool. And we want to have as many fully validating Bitcoin nodes as possible. All right, so you have access to hardware, cheap electricity, and internet connection, and you can mine. Now, you or your software are going to have to answer some questions, right? Which transactions should you include? We already talked about generally wanting to include the highest transaction fees. Which block should I mine on? What do I do if I find two blocks at the same heights, etc. So generally, if you're a miner, you can follow the default answers that are built into the software. But are there ways to maximize our payout by modifying these algorithms? And there has been some research, and the answer seems to be a qualified yes. But these will generally have a negative impact on other users, which is why we'll call them attacks. They're not direct attacks, but they're attacks really on the network itself. So a forking attack, basically a double spend that goes back multiple blocks in the blockchain. So you as a miner try to build upon a previous block in the blockchain to create an alternative chain. This is very easily detectable and would require a large amount of hash power. So it's not something that is too much of a concern. Here we can see in block sub 2, Alice sent a transaction to Bob, and now as a forking attack, we're going to try, instead of building off block sub 2, build off block sub 1. So we now have block sub 2 prime, where Alice also sends a transaction, but she sends it to a different transaction that she already also controls. And so just like a 51% attack, we're going to see that we're going to try to make a new chain be the canonical chain by adding more proof of work to it. So although here, generally when we think of a 51% attack, it's going to be something that's very quick right after the blocks are produced. But assuming you have enough hash power, you could do this arbitrarily far back in the chain. We don't have to do this ourselves. We could, bribe others, out of band, off blockchain, off chain, go to some of the biggest pool managers run and ask them to help you out and follow your chain, or run a pool at a loss. So you could pay people to join your pool. you could leave big tips, right? So like really big transactions with high transaction fees that are only valid on the forked chain. So there are a lot of different ways, and we actually see, I have a link to what looks like this happening in the real world, lots of ways to entice others to follow your chain instead of what was actually the canonical chain. Block withholding. So remember, we generally expect if you create a block that you're going to announce it immediately to the world because this makes the most sense. But what if you held on to your block and then without broadcasting and try to build a second block on top of it before you broadcast it? Well, what this means is that you are suddenly 2 blocks ahead of the network and all the hash power they've been using is wasted. So this is called selfish mining. I mean, you think about it, all mining is in a sense selfish since the actors are rational. But all the other blocks that people have produced are immediately orphaned and you've already got a head start on creating the next block. And it turns out that if you have over 25% of the hash power on the network, block withholding may actually be a valid strategy. Although once again, we have not really seen this on the Bitcoin network itself. Although we have seen similar attacks on other networks. So here we can just see a diagram where the selfish miner creates block sub 2 and block sub 3. So all the miners who generated block sub 4, the one who built on block sub 4, and any trying to build on top of it, all of that hash power was wasted, which means that they spent all this energy on proof of work, but they weren't able to actually get anything out of it because that block 4, any block rewards from that are not going to be valid in this new canonical chain of block sub 1, sub 2, sub 3. There's punitive forking. So we've already discussed in especially like Goofy Coin and Scrooge Coin, blacklisting particular addresses. But if we have a decentralized system, as long as that transaction can get out, and there are ways of stopping that too, but as long as it can get out into the transaction pool, it may take longer, but someone else could include it in a block. But if we have sufficient mining power, let's say we have an overwhelming amount of mining power, we can tell people, hey, if you include that transaction, then we're not going to consider your blocks valid. Okay? So we will always just try to get ahead of you and ignore the blocks that you produce. So this is called punitive forking. Like we are going to fork in a different way if you try to include any UTXOs or addresses that we have blacklisted. So let's say we have this evil transaction, whatever your definition of evil is. Someone includes it and we say we're going to ignore evil transaction. So we create block 2 prime, 3 prime, 4 prime, etc. And anytime someone tries to include those evil transaction in a block, we just ignore it and fork away from it again. So this is really only an issue if you have an overwhelming majority of hash power. Otherwise, it's a real waste of time. Because remember, you have skin in the game when you are producing blocks. So you end up wasting your hash power on a chain that nobody else is following. And the blacklisted transactions are going to go through anyway on the main chain. So punitive forking can often be problematic. So feather forking means you'll attempt to fork, but eventually give up if you can't do it. So you tell people ahead of time, look, I'm not going to mine on this, but if you can't do it, you decide that, all right, I'm just going to go back to your chain. The probability of success for this is alpha squared, where alpha is your percentage of the hash power of the entire network. And it's alpha squared because you not only need to produce one block before everyone else, but you need to get a block ahead of everyone else. You need to generate 2 blocks so that your chain ends up actually being longer. So assume that you have 15% of hash power, which many pools already do. So your probability of a successful feather fork is pretty low. It's 2.25%. But if you're another miner and you don't really care about this evil transaction, will you take the risk that your blocks, may, the blocks you produce may not be considered canonical? In general, we have not seen any major feather forking attacks on Bitcoin. It's proved pretty resilient so far, and it seems like there would be a lot of community anger at anyone that tried to do this, since uncensorability is sort of one of the key components of Bitcoin. But it certainly is a possible attack. So I hope this gave you a better understanding of how mining works, specifically in Bitcoin, and not just from the theoretical perspective, but what's actually happening in real life. So thank you, and I hope you enjoyed this special edition of Blockchain Fundamentals.